Hello, this is Meg Galloway, and I would like to thank all of you who, sorry about that, all of you who stuck with us through our slight technical problems at the beginning. And I'd like to thank you for joining this presentation of 2D modeling parameters that is being sponsored by HDR. So without further ado, I would like to jump into our first session that's presented by Sue Hoegberg, who is a senior GIS manager with Dewberry, and the name of her presentation is National Elevation Requirements and Benefits Study Preliminary Results. Enjoy the session.
My name is Ashley Chappell from NOAA, and I'm here with my colleague Sue Hoegberg from Dewberry. And we're presenting on behalf of Allison Jason and Carol Ostergren from the USGS. So we're going to talk today about the 3D Nation study.
Okay.
And Sue and I did present on this last year at ASFPM in Cleveland. So hopefully you've heard about 3D
Sounds
Nation
good.
or you participated in the study
we're rolling
yourselves.
now.
But if
And I can
not,
see
just
we
know
are.
that the vision of 3D Nation is a United States that has the elevation data it needs to be a truly GPS-enabled nation, where we have that elevation data that's so key, from the peaks of our mountains to the depths of our oceans, that boosts the economy,
Okay,
protects our lives and livelihoods,
Thanks.
makes our communities more resilient, and so much more. So I'm going to talk about the background of the study and how we got here, the goals of the study, and then hand off to Sue, who will cover what we asked in the study, preliminary results from our questionnaire, and where we're headed in the future. Some of you may have actually participated in the National Enhanced Elevation Assessment. That was really the foundational study of elevation data that we are building on today. So the NEA study back in 2011, 2012 asked many entities, many stakeholders, federal, state, local, tribal, not-for-profit, private sector, asked all of these respondents some of similar questions to what we're asking in the 3D Nation study, but pretty much, what are the mission critical activities where you need elevation data, and what benefits would accrue to you if you had that data? Over 600 plus mission critical activities resulted, and 1.2 billion to 13 billion in benefits annually if people had the elevation data that they needed. So this study was kind of earth-shattering, if you will, and led to looking at scenarios for how to best meet those many requirements that were received in the study. Cost-benefit analysis of requirements and benefits landed on quality level 2 data meeting the most needs at the least cost. And so that is the genesis of kind of the quality level 2 mindset that we've had since then. And the 3D elevation program took that and ran with it. And you're probably all familiar, many of you are familiar with the successes of the 3D program as it has marched across the country, acquiring terrestrial topographic LiDAR data. And so building on that is what we're trying to do with the 3D Nation study. So the coastal and ocean mapping agencies, some of which are the same as the terrestrial mapping agencies in the case of the USGS and NOAA to some extent, Army Corps. But on the coastal and ocean side, we wanted to undertake a NEA-like study ourselves. And it happened at the time that the 3D program wanted to revisit and check in, kind of a performance check of how it was doing, as it was 5 years into its program. So we merged efforts. We became a 3D Nation study, which I actually think is even better than doing 2 studies separately, merging the 2, looking at elevation data holistically, like I said, from the tops of the mountains to the depths of our oceans, but understanding how those elevation data needs intersect, integrate, particularly at the coast. that coastal zone, that very dynamic region where you need to know depths of water and elevations of the beach and higher for storm surge, for flooding, for many other things. And we did the study in a very technology agnostic way where we said, let's take technology out of the equation. Don't worry about the limitations of technology today. Don't worry about what you know that topographic LiDAR sensors can accomplish or multi-beam sonar can acquire. Just let's take those out and just focus on the data itself. When do you need it? Where you need it? How accurate does it need to be? Those kinds of questions, not what you think technology can accomplish for you. And so the results of this study that Sue is going to talk about in just a second really will guide the next generation of the 3DET program and the ocean and coastal mapping agencies. The products and services that we deliver will be guided by the results of this study and the same kinds of scenarios that the NIA used to land on quality level 2 and the progress it's made in accomplishing the acquisitions that it has. Now I'll turn it over to Sue, who will continue with more on the study itself.
Okay, thanks. So those of you who participated in the study may remember that we had a very long and complicated online questionnaire where we asked what seemed like 1 billion questions about people's requirements for inland topography, inland bathymetry, nearshore and offshore bathymetry. We asked about the geographic extents of their mission critical activity. And so we're calling this the area of interest. And we asked about it so that we could essentially tie all of the other information that we were collecting to geospatial polygons so that ultimately we can do some spatial analysis. We asked a lot of questions about the requirements of the elevation data that people need to perform their mission critical activity. So what's the quality level of the data they need? How frequently do they need it updated? What's the acceptable level of horizontal and vertical error? How far up and down the beach profile do people need data in that blended coastal zone? What kinds of hydrologic processing do people need? Is tide correction important? Another one that's a big concern is how seamless do the data need to be within each data category. So between essentially flight lines or tiles of topographic data or bathymetric data, but also where those types of data from different sensors meet. How seamless does that need to be? What kinds of data products are people looking for? And then in addition to the requirements, we asked about what kinds of data people are currently using, what kinds of benefits they're receiving from those data that they're currently using, and what future benefits would they be likely to receive to their program if all of the requirements that we asked about were met. And we asked about those benefits in these different categories of operational, customer service, and societal benefits. So this is just a graphic showing where we are in the study process. We are wrapping up our data validation process right now. So we spent some time designing the study, developing the questionnaire, getting OMB approval for the questionnaire. Then we had the questionnaire open and asked representatives from all 50 states, 48, I think, federal agencies, and a number of nonprofits and private entities. Then we went through a two-phase validation process, and we'll talk a little bit more about that. And we're, as I say, wrapping up the data validation process. And then next is going to be the actually really fun part, is where we actually get to look geospatially at all the information that we've collected, try and take a look at the requirements and the benefits and see where there are hotspots of requirements, where there might be hotspots of benefits, stack all of those things up and look at what might make sense in terms of program scenarios where we meet some, most, or all of the user requirements. What would it cost to deliver that kind of each one of those kinds of program scenarios? And what would be the benefits of delivering each of those program scenarios? So like the NEO, we'll be making some recommendations about what would make sense based on the information that we've collected. So here's a little bit more on where we are in terms of the process and these validation steps that we took. So for the states, after we had the initial questionnaire responses, we conducted validation meetings with each of the states. Then after the state validation was completed, we did a regional review, and I'll show you a little graphic about that in a second. Right now, we are just finalizing the final draft summary reports, and we'll show you a few results based on pretty much where we are with the states. And for the federal agencies, we also conducted the validation meetings with each of the agencies. We are currently in the middle of doing some group reviews. So the preliminary results that we're going to present don't reflect any changes from the initial questionnaire responses for the federal agencies and the non-governmental agencies. They are also in the process right now. This is just an illustration of the regional reviews that we did with the states, where we grouped the states and highlighted by region where states maybe had some gaps in their responses. So for instance, and we could also see where there might be a hole, like here, there's like all the other states in the Great Lakes said they needed elevation data for water supply and quality, except for one. So, you know, what's wrong with this picture? Should this state have reported, potentially reported water supply and quality as an important business use for their state? So we went through and presented these to the states and asked them if they wanted to, what we called, adopt a business use based on this look. And so here's the before of the Great Lakes region and the after the states adopted. So you can see that a lot of these red highlighted areas where we thought maybe one of those business uses really might be important to one of the states, and the states actually agreed and said, yes, we do think that would be an important use of elevation data for us. So that's just the kind of validation that we've been going through. And we're doing a similar look at the federal agencies, not by region, but by grouping of, so like the Department of Agriculture agencies all together and the Department of Defense agencies all together. So this is where we are with some of our preliminary results. This is a breakdown by organization type. So we're looking at federal agencies, state, regional, local and tribal government, not-for-profit and private entities. Before we did our validation, so raw from the questionnaire responses, we had $1.4 billion in annual benefits. And you can see that the state and regions have significantly increased since then, and we're up to about $7.8 billion in potential future annual benefits. By geography type, here's a breakdown of where it looks like the benefits would be coming in terms of inland topography, inland bathymetry, nearshore bathymetry, and offshore bathymetry. And those have all increased somewhat significantly since we started the validation process. I think we have a little more to go in that regard as well. Business uses, we have a lot of movement in terms of business uses, and you can actually see that in some cases, the number of mission critical activities actually changed because part of the validation process also included consolidation of responses. So in some cases, there were multiple respondents from a state or a federal agency that were talking about essentially the same activity. And this was in particular for the federal agencies, where you can imagine that the Army Corps of Engineers maybe had multiple respondents from different districts, all talking about their flood risk management activities, or their dredging activities. And instead of looking at each of those individually by their district, we wanted to look at them across the nation by the agency. After validation, you'll see that forest resources management actually came into the top 10, and it wasn't before. Pretty much there wasn't a lot of change in terms of the top 10 business uses. And this is, a map view of the before and after the regional review. And you can see that we pretty much doubled state and local government responses. We're not quite sure that at the federal level we'll have that dramatic an increase, but we do expect some increase at the federal level as well as we finish up our group review. And this is showing a breakdown by geography type of our quality level and update frequency requirements. So this is for inland topo. You can see that the predominant requirement is still for quality level 2, but a pretty significant number of respondents need something higher than that. So actually more than half need something higher than that. And pretty much across the board, the consistent update frequency requirement, it was 4 to 5. The highest response was 4 to 5 years, with a pretty even split between 2 to 3 years and 6 to 10 years, which is sort of interesting. For inland bathymetry, so this is a new data category that isn't currently included in the 3DEP. But the quality level requirements are for quality 0B predominantly, but also quality level 1 and quality level 2. And I'll just say that the inland bathymetry quality levels are not, they're meant to mirror the topo quality levels, but they don't actually represent exactly the same vertical accuracy. Again, 4 to 5 years, update frequency most predominant and kind of evenly split between 6 to 10 and 2 to 3 years. Nearshore bathymetry, quality level 0B again, highest requirement, and 1 and 2 for the next 2 highest. And offshore bathymetry, pretty good mix here of different requirements, which makes sense because there is such a huge variation in how far offshore people need data, which also speaks to what IHO order would be most applicable. So next, as I was saying, that we're going to be spatially looking at all of the information that we've collected. So not only looking at data that's provided by states individually, but also once we have everything, we can stack all of those mission critical activity areas of interest on top of each other and look at not just what state agencies in a given state have asked for, but what are the overlapping federal and non-governmental requirements in that state as well. And that'll just be hugely interesting in terms of where we can make some assessments and program scenarios. So again, as we finish up our state and local and government responses and our federal government responses and our non-governmental responses, then we will be able to do that aggregation of just what the states want, what the feds want, what the non-government government entities want, and then do that spatial analysis cookie cuttered in different ways. So cookie cuttered by state or by region or multiple different ways. So this is pretty much, what we're saying is the last chance for folks to weigh in. If you're representing a state, you can expect to see a draft final summary report coming your way shortly. If you're with a federal agency and you haven't sent in your group review, please do so soon. And if you're representing a private or non-governmental entity and you're interested in participating, we would love to get some additional input from you all. We're particularly interested in a few business uses that we've noted here in particular, where we think that we may still be lacking non-governmental responses from the recreation industry, the private transportation industry representing folks who are developing smart cars and that sort of thing, renewable energy, precision farming, fisheries, and oil and gas exploration. So if you have any folks who you think should participate who haven't, please send a point of contact to me and I will be happy to send out information on how they could participate in the study. So, as I said, we're wrapping up the validation process. We will be consolidating all the information that we've collected once we have finished the validation process, doing that spatial analysis of the responses, and developing key requirements and benefits that will help us develop different program scenarios, and then doing the analysis of benefit, cost, and return on investment for the program scenarios we choose, which would be, essentially national program scenarios that meet some, most, or all of the user requirements. And, we expect that, the scenario where we meet all of the user requirements, which might be quality level 1 every year, probably not going to be affordable, but somewhere, in the middle, we think there will be a sweet spot where it would make sense to move forward with, the next generation of a program to collect elevation data. We'll be publishing a final report, and then NOAA and USGS can look at what makes sense for them in terms of determining their program direction. So thank you. And Ashley, did you have a few other things you wanted to mention?
Yeah, I just wanted to say thanks. Thanks for listening. Thanks for to those of you who participated in the study. And I did want to echo Sue's flagging of your last chance for providing input. She her slide just before this ended with a statement about determining program direction, and I hope that people understand that it's this kind of study, just like the NIA study did, this 3D Nation study will have an impact on how federal agencies will pursue the acquisition of elevation data and what requirements it will meet in the future, using this study as one of the guides. And if your requirements, your benefits aren't included here, that could influence the outcome of the scenarios and perhaps miss sectors of the economy, of industry, of.
I'd like to thank Ashley and Sue for that wonderful presentation, and I'd like to thank all of you for sticking through our little technical glitches at the beginning. We do have some questions that have come in, so we'd like to take the time remaining to ask those questions, as many of those as we can get to. The first one is from Timothy, and the question is, where is the significant benefit coming from for state and regional users, and why are similar increases not shown at the federal level?
Well, thanks for asking that question, and we may not have clarified that as well as we could have. We are going through we talked about having gone through this regional review process for the states, and that generated a lot of additional benefits and requirements, and sort of fleshed out the picture for them significantly. And we are going through a similar process right now for the federal agencies. So we did, instead of doing it regionally, we grouped the federal agencies by sort of larger department, so Department of Transportation, Department of the Interior agencies, agriculture agencies, energy agencies, that sort of thing. And we haven't received all of those responses back yet. So the additional benefits that came in through the regional review for the states, the corresponding federal just hasn't yet been tabulated. And I see that there's one other question about private industry, and we did reach out to the private industry and not-for-profits. We got some responses, although not nearly as many as we thought we might get. And we are still looking for additional input from the from the private industry. So if anybody is interested in participating, we'd be very happy to send you an abbreviated template that you could use to send some information in. So you could contact me, and I'd be happy to get that out to you.
Okay. I think we have time for at least one more question from Brent. Is there any advantage or benefit for a community to offer its full watershed grade 1 LIDAR to the national map?
Well, certainly from the perspective of map once, use many times, you know, and from the perspective of not wasting resources, absolutely. The USGS will combine data submitted by others into the national map surface, and I'm sure they're wonderfully happy to get contributions from local communities.
Well, thank you so much, and I think we need to move on to our next presentation. But again, thank you to Sue and Ashley, who wasn't able to join us in the live stream.
Thank you.
Okay, and now something I should have done at the beginning, but with our start and stop, I missed, and that is for those of you who didn't know. The question and answer session, we're getting our questions from the chat box. It should be showing up on the right side of your screen. So please, if you have a question during the presentation, put it in, and we will filter through those and try to get to as many as we can at the end of the session. If you see a question that you like, hit the like button, and it's more likely that that will be one of the questions that are chosen if we have too many to take in the time. So now I'd like to go to our second session. The title of this session is Impacts of 2D Parameters, an XPSWMM Case Study. And the presenters are Brandon Hilbrich, who's a Water Resource Manager at HDR, Jeremy George, who's a senior engineer with the City of San Antonio Public Works Department Floodplain Management Team, and Matthew Anderson, who's a project manager with Innoviz. Let's look at the presentation. We'll be back for questions at the end.
Jeremy, Matt, and I would like to welcome you to the second session of Track G2 2D Modeling Parameters. Today we'll be discussing 2D parameter variability from a XPSWM case study. Just a quick overview. Jeremy's going to start us off with just an overview of the 2D modeling parameters in general, and then we'll get into our case study and discuss a little bit of the background, some results, and some findings and trends that we found from all the results put together. And then we're going to wrap it up with Matt talking about some new things coming with XPSWM 2020 and how some of those changes can help with some of the things that we found during our case study.
Thanks, Brandon. So the idea for this presentation came from an ongoing conversation among some engineers local to San Antonio, and as a model reviewer for the city of San Antonio, I'm tasked with reviewing two-dimensional models, and sometimes I'm asked about 2D modeling guidance and how varying certain parameters might impact model results. So Brandon and I decided to put together a few case studies and a presentation that explored several different 2D parameter inputs in Innoviz's XPSWM software. The original version of this presentation was actually 3 case studies, but in the interest of time for today's presentation, we had to limit ourselves to just this one case study you'll see here in a moment. So first, what is a parameter? Well, Wikipedia has a definition for this as it relates to engineering, and they state that a parameter is generally any characteristic that can help in defining or classifying a particular system. A parameter is an element of a system that is useful or critical when identifying the system or evaluating its performance. So in modeling, a parameter is an input that helps define the simulation, but is usually constant for the duration of the simulation. So although specific 2D modeling parameters can and do vary with each 2D modeling software, there are a number of parameters that are represented in one form or another by most of the 2D softwares. Some of the most common parameters are typically the 2D cell or element size, a 2D surface roughness, a 2D grid orientation, or an underlying terrain information. But for this case study, we'll be exploring how varying 2D cell size and 2D land use, and land uses represents the surface roughness in XPSWM, and the computational engine impact model results. A rainfall on grid application over a watershed subbasin with steep terrain was used, and the rainfall on grid feature is the one that I often get results about, particularly as it relates to the city of San Antonio accepting it as a valid method of introducing flows into a 2D hydraulic model. So these items that just highlighted here would be the main ones we'll be looking at. So let's get on to the case study. So the questions that we asked ourselves for this case study are, how does the 2D grid cell size impact results? And what impact does the type of 2D land use application have on results? And how do the results vary between a classic and extreme 2D engine? So this case study uses XPSWM version 2019.1.2 to run the simulations and generate results, but Matt will introduce a version 2020.1 into the comparison towards the end of the presentation. It's worth noting, though, that this case study is solely a comparison of results, and our intent was not to calibrate the 2D results to HEC-RAS or HEC-RAS. As previously mentioned, we evaluated sensitivity to 3 model parameters. We utilized 7 different 2D grid cell sizes ranging from 15 feet to 100 feet, 2 different 2D surface roughness applications, both static and varied, and 2 different computational engine options for a total of 28 simulations. Innoviz actually offers 3 2D engine options, a classic, an extreme CPU, and extreme GPU, but we opted just to use the classic and extreme GPU because they're considered the slowest and fastest, respectively, from a CPU runtime perspective. So a little background for the case study before I hand it off to Brandon. This subbasin we chose for the case study is approximately 1 square mile in size, and it's located within the Leon Creek watershed in the far northwest side of Bexar County. The subbasin encompasses Helotes Creek over here, and then, Helotes Creek tributary A, and then unnamed tributary 1 to Helotes Creek tributary A. And the basin is partially developed. And as I mentioned before, the case study utilized an area with steep terrain. And these contours that you see in this image over here are actually 10-foot contours. So you can see just how steep the terrain is in this area. The 4 model results that we evaluated were peak flow from the subbasin. So generally we measured it down here in the downstream end, time to peak, volume left on the 2D grid, and the CPU runtime. And here, I'll hand it off to Brandon.
Thank you, Jeremy. So we started off by downloading getting the latest effective HMS model for the watershed. And so the drainage area that we picked that Jeremy mentioned, it's about 1 square mile. The slopes in the watershed are pretty steep, but the overall tributary slopes were averaging about 3.5%. The watershed is mostly undeveloped with those small areas in the southeast area that do have some development in there. The hydrology parameters were developed using curve number loss method and then the Snyder transform method. And the initial effective results showed the 100-year peak flow at 2,600 CFS with a time to peak around 1236. So in our initial XP model development, we used the available LiDAR terrain to develop our surface, and then we pulled the effective boundary for that watershed to define our model extents. And the 2D land use was defined using the same spatial land use that was used for hydrology. However, some refinements were made to the land use to provide a little more detail as far as the 2D surfaces. The initial grid cell size that we ran was a 50-foot grid cell, and then we used a static land use approach for this first run, just to get an idea of where we were at. The excess runoff hydrograph was pulled from the HMS model, and that was used and applied to the 2D surface for the watershed. As you can see from our initial first run results, the peak flows were just over 60% higher than the HMS results, and the time to peak was 16 minutes shorter. And so our initial thoughts were, okay, why the big difference there? We looked at the overall volume being applied to the surface versus what was going through the system, and the volumes were matching up pretty well. So we're wanting to use HMS as just kind of a baseline. Again, Jeremy mentioned nothing about we weren't going to calibrate to it, but we just wanted to see some comparisons. So we took a look back at the HMS parameters and started going through, okay, what are some things that could have happened on why these results were different. First thing we noticed was the basin delineation versus the true basin divides on the terrain aren't exactly overlaying each other, especially when you have a 50-foot grid cell size. There's some coarseness there. So a little bit of volume was leaking outside the basin collecting on the edges of the grid, but not near enough to have any sort of marginal impact on overall volume. So the next thing we looked at was the transform parameters. And what we did was we looked at the 2D results and used that to help inform our flow path, and looked at adjusting the lag time and peaking coefficients based on the local guidance, which was the City of San Antonio Drainage Criteria Manual and the City of Bernie Subdivision Ordinance. And based on the revisions that were made, our peak flows came in a lot closer between HMS and the XP, and the time to peak got a lot closer as well. So we felt like that was a good adjustment, just having that way we had a relatively good comparison moving forward with all of our different runs. So we continued running the rest of the cell sizes that we mentioned earlier, 15 foot to 100 feet, and started to make some comparisons with our results. The graph to the right is showing both classic and extreme run results, showing peak flow versus cell size and volume remaining versus cell size. As you can see from the results, the results vary plus or minus with the HMS. The result that proved to be the closest to what HMS was showing varied between the two, classic being the 50-foot cell size and extreme being the 70. But one thing you can notice is that the peak flows, you don't see that much variation between the 15-foot to 50-foot, and then you see a significant decrease or a change in the results. And same can be said about the volume remaining on the surface in the system after the simulation run. We took a look at the volume remaining because that one you can see a consistent change as the cell size increases. And what we found was, as you would expect, as the cell size increases, your detail and definition of your surface gets more coarse, and so there was a lot more areas of stored volume in depression areas or where cells just couldn't drain. Also, the simulation time was set to 24 hours just for this case study, but there was still some volume remaining on the surface due to it not making it all the way through. So you could extend the run to get more of that volume through there. And then, as I mentioned earlier, we did still see some volume collecting along the edges of the grid that it fell outside of the boundary extents that were defined by the effective subbasin. Moving forward, looking at time to peak, you can see that as the cell size increased, the time to peak also increased. But so the larger the cell size, the closer you got to the HMS time, but that's not necessarily a good thing. As the cell size increased, the surface becomes more coarse, your flow path loses a lot of the detail, and so your rate of change in conveyance also decreases, which causes that time to peak shift. The one thing to notice is that from the 15-foot cell size to the 50-foot, you don't see a lot of change in time to peak. And just in general, overall magnitude of differences, you're only looking at a 6-minute difference in time to peak between the smallest cell size versus the largest cell size. So if you are calibrating a model or trying to validate some results, you can see here that cell size, it does have an impact on your peak timing, but the overall magnitude is not that much. And so if time to peak is one of your target values that you're trying to calibrate or validate to, the 2D cell size may not be the only parameter that you need to mess with to really hone in those results. Looking back at the hydrology parameters would provide more influence on the overall impacts of that time shift. So moving on to the varied results. As Jeremy mentioned, we used a decay function from the ICPR version 4 user manual to define our changing in values from shallow depths of 0 all the way up to greater than 5 feet. You can look at the image on the right, and that's some results pulled from one of the static runs, and that shows depth variation from 0 to 2 feet. So there's a lot of shallow depth flooding in the watershed from those static runs. So you're going to expect to see some differences in results when we start using a varied land use curve when shallow depths provide more of an influence on overall impacts. One thing to note is that between classic and extreme, the extreme runs do limit the number of entries in the varied land use to 8. So if you are going to go from a classic to an extreme, you do have to break down your equation to only 8 data points. Looking at some of the results, so right now we're showing just classic, and this is static versus varied land use. The static is the solid line, and the dashed lines are the varied land use results. You can see overall, as you would expect, more shallow flow, higher in values, overall peak flows decreased for the varied land use, and the volume remaining in the surface increased. But you will notice that the overall trend across the increasing cell size didn't fluctuate much between the static versus varied. The overall change in peak flows and change in volumes remain roughly the same, going from the 15-foot to the 100-foot cell size. Now adding in the extreme results, you see similar trends between extreme versus classic, static versus varied, going from your smallest to your largest cell size. The one thing to note is that the extreme results did produce higher flows for both static and varied. And part of that is due to the equations that are used, the classic using the finite difference second order, whereas extreme uses the second order finite volume equation. And TrueFlow actually does have some language in their manual about going from classic to extreme, how there may be some calibration to your n values that are needed to adjust based on the different equations that are being used. But again, looking at the extreme results, the volume remaining on the surface, investigated what was going on there, and similar to the classic, there was still some volume that would hang on the edges of the grid that got outside of the delineated subbasin. And then same thing with the just some cells not being able to drain due to the coarseness of the grid as you got larger. Looking at time to peak between the static and varied, the both showed an increase in time to peak, so that as that grid cell gets more coarse, the overall time to peak slows down due to less definition in the overall tributary moving through the watershed. One thing to note is that the difference between the varied versus static increased as the cell sizes increased. The differences in the 15-foot were 3 minute versus an 8 minute for the 100-year. So as cell size did increase, that the rate of change did start to diverge between the two results. And then adding in the extreme results, you would see similar characteristics to the peak flows. Overall peak flows with extreme were slightly higher than classic. So naturally, their conveyance is more efficient. The time to peaks were a little bit lower. And that's where that if you were calibrating, that tweaking of those n values may be necessary to going from classic to extreme to get your results to line up a little bit better. But one thing to note here is you'll notice with the extreme, the time to peak did not change at all until you got until you got larger than the 50-foot grid cell size. So again, going back to when you're doing sensitivity analysis of your model, determining what's the optimal cell size you want to use. From this example, you can see timing did not have much of an impact when you're looking at a 15-foot up to a 50-foot cell size. And you can see the rate of change decreased as well with the extreme. Previously, the classic had a 3-minute difference on the small end and an 8-minute difference on the large end, whereas here we're showing a 2-minute versus 6-minute. Overall run times, the table to the right shows number of grid cell sizes with number of grid cells within each model to give you a order of magnitude. And you can see there's not a lot of difference in run times between the 40 and the 100, but once you get to that 30 versus to 15 grid cell size, there's an exponential increase in computational runtime, anywhere from 3 to 4.5 hours for the classic. And if you look at a rule of thumb for this run, if you divide the cell size by half, you're going to increase the runtime by 4 to 5. Adding in the extreme, obviously running with extreme has a lot of benefit as far as CPU runtime. We were able to reduce the runtime over 90% for the 15-foot results. Same thing you see between the 30 and 15-foot cell size. There's a difference in runtime of 13 minutes, whereas between the 30 and 100, there's only a 2-minute difference. So same trend, just overall magnitude of difference. And for this one, for the extreme, dividing the cell size by half, increase the runtime by 2 to 4. So putting that all together, overall, let's go back to the initial questions. How does the 2D grid cell size impact results? Well, we saw that peak flow, volume remaining, and runtimes are all greatly influenced by cell size. And that the best fit is not always the smallest grid cell size or the most optimal one, depending on what is the intent of the model, what is the level of detail of the model, and what kind of calibration data do you have. Next question, what impacts does the type of 2D land use application, static versus dynamic, static versus varied, have on the results? We did see that flow conditions in steep terrain are greatly influenced by the roughness, especially in this case. Between the static and varied land use, flows show differences between 10 and 20%. So that is something to be aware of if you do have this type of situation. And also just understanding what is your modeling intent? Where are you at? Are you downtown urban? Are you out in the rural areas? Things like that will help you have a better understanding. Am I dealing with a lot of overland shallow flows or more concentrated deep flows, which could help decide what type of approach you want to take as far as your land use. And then lastly, how the results vary between classic versus extreme. We did see that there was a general trend of classic showing longer times and lower flows between all the results. As I mentioned, a two-flow does provide recommendations on what you should look for when going from classic to extreme. The extreme did show higher flows and lower volumes, making it more efficient. So if you were calibrating, there may be some tweaking of N values with that extreme runs. We did notice that overall peak flow variations between the range of cell sizes was less with extreme versus classic. So there was less ranges between results through the cell size variation. And then again, just making sure you understand what is your intent in where you're at and what you're trying to do. Are you focused more on shallow urban flows or more on concentrated tributary type flows? And then the most obvious variation was the computational runtime and the benefits of using the extreme versus the classic. So now I'm gonna switch over to Matt and let him kind of touch on the latest 2020 version.
So just kind of want to recap a little bit, right? You know, you went through those findings there in the 2D grid cell size and the impact on its results, right? As we get larger grid cells, we lose resolution, right? And based on the engines, right? The classic engine is a finite difference. It's a uniform time step, right? It looks at everything at that same aspect. Where the extreme, it's a finite volume calculation. It's adaptive. So if water is flowing across a cell that is steep, right, it's going to compute those time steps as appropriate, right? So how do we address some of that? We can address some of that a little bit with potentially uniform cell size, right? That's one of the other findings. That uniform cell size on runtime, you know, in the classic, I think, 4 or 5 hours there, and that's the number of computational cells, if you will. The speed difference between 14,000 cells and 100,000, or in this case, 159,000 cells, really has an impact. Well, hardware also impacts that, CPU versus GPU, the two extremes there, right? So how can we, as XPSWM, how do we help, right? So the preview 2020 is there are two features. One of the first features is what's called subgrid sampling, okay? And this helps eliminate some of the convergence issue that you kind of see, based on those cell sizes. We have, as Brandon indicated, potential for trapped water on the surface. So in the non-SGS face, both the back face and the my left face there are dry, right? So the water doesn't transmit to that back face or the left side face. But as soon as I turn subgrid sampling on, which queries the underlying terrain, we have now 4 wet faces. And that's something that's coming in 2020 to allow the user to get a more detail in each grid cell than just trying to assume a flat bucket, if you will, right? That SGS, the subgrid sampling, gives us that ability to indicate, hey, water actually does flow out the wet, both the back as well as the left side of that face. The underlying volume and wetted perimeter and the channel and the edges of that grid cell now all become engaged. Well, that's going to have an impact on the resolution of those results. Well, the other thing that's coming in 2020 is what's called quad tree meshing. In this case, it's a multiple domain workflow, and you can kind of see that in the image there. We have varying grid cells in one model. So they're not always that 50-foot grid cell. They can go 40, 20, 10, 5, right? So it's a quarter every time. Each time a grid cell, gets smaller, it's going to cut it in 4, right? So you're nesting cells hopefully where you need the detail. So in the image there, you've got more detail around bridge openings, right? You've got a little bit higher detail around the channel area, and then overbank areas there may not need that detail. So those are two approaches to address some of those issues. So if we take a look at this watershed again, so there's that 50-foot extreme run, right? And in this case, I think Brandon's images earlier showed a foot, the depths a foot or greater, right? In this case, I've dropped it down to 0.7. Shows you quite a bit more wet cells, right, where there is some capture. And in fact, as Brandon indicated, there are some areas along those edges that do appear to capture water, right? We didn't use the watershed as an external boundary, so those do get caught up in that. So when we take SGS on, that's that center image, we get we sample that terrain at 5 feet. And I think the LiDAR terrain is actually a 3 foot or a 1 meter resolution. I had resampled this at 5 feet for these model runs, so slightly different results. But you can kind of see there's a lot less water that is trapped by the grid cells. So that impacts, our results a bit. We get a little bit faster time to peak, right? And quite a bit higher Q peak, but we take about 3 minutes additional runtime. Now I put the little tilde there because the first time you sample that run, it takes a little bit of time to read all of those elevations. The next time, because of caching, we don't need to resample that unless we've changed the underlying terrain. So it anywhere can be between roughly 3.5 to 5.5 minutes on that. So it varies depending on which run you have. Now, quad tree. Now I've also run SGS with the quad tree. We get a much different view. We get much higher resolution in what is 0.7 of a foot or greater, right? So that quad tree, we're allowed to then refine, okay, and I did one single level 3 domain. So these cells here, the really tiny ones there, are 12.5 feet, somewhat close to, I think, the 15 feet that was originally run, which produced roughly 160,000 grid cells. But you can kind of see that quad tree, we've got a pretty high resolution in that area that could be of interest in that, right? So, and that only ran on the GPU for about 16 minutes, right? So, and I think runtime for that 15-foot was about 19. So pretty comparable, right? It's a rough number of grid cell sizes in that. So those are two of those things that are coming in XPSWM 2020.
Thanks, Matt. So let's transition over to wrap up this presentation with some overall apparent trends and takeaways. As true with most hydraulic models, as the software advances with features and capabilities, there may be more parameter knobs to understand and utilize. We found this to be true with XPSWM and the new SGS and Quadtree features that were touched on a little today. Just by adding these two features alone to the discussion, we discovered that this one case study could be significantly expanded to try to glean even more definitive trends. And that was just one case study. So we saw with this case study that the results were heavily influenced by 2D grid cell size and then followed by 2D surface roughness application. However, the new SGS and Quadtree features might provide increased flexibility to refine these sensitive areas rather than having to change the 2D cell size globally throughout the model. It gives us more flexibility from refining just localized areas. We also learned that simply switching the computational engine might require an additional sensitivity analysis to understand the potential model impacts. But lastly, even though it wasn't an objective of the case study to explore parameter calibration, of the variation of results in the case study trends affirm that calibration could be key if calibration data is available. And so with that, here's our contact information in case there's any follow-up questions, and we'd be happy to take any questions now.
I'd like to thank Brandon, Jeremy, and Matthew for that very informative session. We do have a few minutes for questions, so I'll dive right into them. The first one is from Mark. Aren't the differences between HMS and XPSWM due to HMS using approximate hydrologic methods versus XPSWM using more rigorous hydraulic methods?
Yes, that's correct. In this case, we did not have the HMS model did not include any routing functions. It was just a sub-basin. So all you had was your initial basin parameters, your Snyder transform method. So in this case, the differences between the transform between the HMS and the XP had to deal with how accurate the Snyder time was. And as we mentioned, we did go back and do an adjustment to get that flow path more correctly defined based on what we were seeing in the XP model. But at the end of the day, we weren't trying to calibrate the HMS or the XP to one or the other just because there weren't observed data points out there to begin with. It was more of a sensitivity analysis and just understanding the impacts of varying some of these parameters.
Thank you. The second question is from Jeff. What's the difference between classic and extreme GPU?
Yeah, so in XPSWM, we have two formulations of the 2D, and we call it XP2D Classic, which is a static time step, so user defined. It is a finite difference solution. What we're calling the XP2D Extreme engine is a finite volume solution. It is an adaptive time step. And it runs on a multi-threaded CPU, or it can be accelerated with your NVIDIA graphics card, your GPU.
Okay, and the third question from Anonymous. Why would the volume remaining be lower with a small cell size? Would you be picking up more depression in the landscape with small cell size?
So smaller cell sizes actually allows you to pick up the positive flow pathways more accurately. So it allows you more definition from all areas of the basin or the areas to your downstream point. So generally speaking, a smaller cell size will allow more conveyance on the grid. And you might have more noise on the grid as far as ponding, volume, ponding depths, but generally that volume is less than at a larger cell size.
Okay, I think that's all the questions we're going to have time for. Again, I'd like to thank Matthew, Jeremy, and Brandon. I will say that it didn't remain up at the end, but there is contact information for each of the gentlemen at the end of the presentation, and we expect that the presentations will be available on a website within a week or so after the conference, and you'll get an email on linking to all the presentations in the conference. So thank you, gentlemen.
Thank you, Meg.
You.
Yep, thanks.
Okay, and our final presentation today is going to be from Kimberly Hetrick, and she is a water resource engineer with CDM Smith. And the title of the presentation is A Methodology for Efficiently Developing Large 2D HEC-RAS Models for the Base Level Evaluation Engineering.
In Massachusetts. The co-authors on this presentation are Tim Adams, also an EIT, and Derek Etkin, a professional engineer, both in the Water Resources Group at CDM Smith in Boston. Today, I am going to be speaking on a methodology that we use in our group for developing large two-dimensional HEC-RAS models for base-level engineering. I am going to focus first on the use of break lines in two-dimensional modeling and how they're aligned with certain terrain features and infrastructure. Second, I'm going to discuss where breakline drawing efforts are prioritized in our two-dimensional models. And third, I'm going to discuss the outside data sources that we use in our workflow for generating breaklines. Examples will be provided from several models in New England, and I am going to be emphasizing the Taunton watershed in southern Massachusetts and Rhode Island. So, two-dimensional analysis for approximate riverine floodplain mapping has gained increasing acceptance in recent years. The incorporation of 2D analysis in HEC-RAS version 5, along with access to high-resolution topography data, has enabled 2D analysis for very large watersheds of several hundred square miles, and has allowed for the ability to model grain-on-grid two-dimensional models for base-level engineering, which incorporate both hydrology and hydraulics. In these large approximate models, the rectangular mesh in the models must be kept coarse in order to keep the runtimes in the days instead of weeks. The figure on the slide shows an example of a two-dimensional model from the Taunton watershed that I mentioned earlier. Each cell is 200 by 200 feet, but there are still more than 500,000 2D cells in this watershed. So within HEC-RAS, each computational cell doesn't have a flat bottom, and the cell faces and edges don't have to be in a straight line with a single elevation. Instead, each computational cell and cell face is based on the details of the terrain that it lays over. The model uses the detailed terrain to develop geometric and hydraulic property tables that represent the cells and the cell faces. For example, in the figure shown here, we have a two-dimensional grid with a cell size of 200 by 200 feet. The 2D flow area preprocessor computes an elevation volume relationship for each cell, and it's based on, again, the detailed terrain data. Similarly, each cell face, as is shown here, is evaluated similar to a cross-section and is also preprocessed into detailed hydraulic property tables. The flow of water moving across the faces between the cells is based on this detailed data. Because of this, the modeler is able to use larger computational cells without losing too much detail to the underlying terrain. As mentioned earlier, a large benefit of this is that it cuts down on processing time. So because the calculations for the flow of water between the cells is done at those cell faces, it's very important that the cell faces align correctly with the features in the terrain data. As you can see in the photo here, there's a man-made structure located in the middle of several cells, which could actually impede the flow of water between the cells. However, because of the orientation of the two-dimensional grid, the cell faces allow for water to flow between the cell faces instead of becoming blocked by the structure. The blue line, which is shown in the graph on this slide, is the terrain data along the cell face, and the pink line is the terrain data across the top of that structure. The difference in elevation, which here is roughly 7 feet, can have a huge impact on the flow of water between cells. So in instances like the example shown above, and again the same example here, where the orthogonal grid generated by default doesn't align with certain critical terrain features that can define or restrict conveyance in a model, Break lines can be added by the modeler, then they force the mesh to orient the cell faces along selected locations. Break lines in a two-dimensional model can be drawn manually throughout the two-dimensional mesh. In this example on the slide, you can see that the break line on the right, which is in pink, forces the cell face to align with this structure. So why then is the addition of break lines in a 2D model important, and why is it so necessary to align cell features with certain terrain features? The representation of many hydraulic features found in a certain terrain, such as dams or natural ridges or elevated roadways, are necessary to represent as hydraulic constraints. By representing these constraints to flow, we increase the accuracy of the model in two main ways. First, by modeling more accurate peak water surface levels upstream of the constraint, and second, by modeling more accurate peak discharges downstream of the constraint. To go into a bit more detail, break lines allow modelers to more accurately model peak water surface levels upstream of the constraint. Without a break line, runoff in locations like the one you see here would be allowed to leak through the hydraulic constraint, creating a lower water surface level upstream. And you can see in this example, water is flowing west to east. On the left-hand side, water is able to flow through the hydraulic constraint, but on the right-hand side, where we've added a break line, water is more accurately allowed to back up behind this feature, such as a dam. Similarly, downstream of a constraint, break lines allow for more accurate peak discharges. Without break lines through the crest of a constraining terrain feature, runoff that's otherwise stored upstream is inaccurately allowed to flow downstream more rapidly. In the example shown here, water is flowing from south to north, from the bottom to the top. And I've placed on the right a break line over a dam, which allows the water to back up upstream of the dam. Shown on the left, when the water is inaccurately allowed to flow through the dam structure, when there isn't a break line, the peak flows downstream are very high. Because the break line allows for the flow to be accurately constrained due to the structure, the flows downstream are more correctly attenuated, as you can see in the graph above. So, how do we draw break lines in our models? Drawing accurate break lines generally requires manually tracing what we call the saddle crest of the terrain feature, which is the highest crest which the upstream water has to flow over in order to get downstream. Break lines can be drawn manually, which involves training modelers how to quickly identify and draw break lines at specific locations. This process could be automated in some instances, but this does present challenges when break line locations don't follow textbook examples, and I'll go into a little bit more detail on that later. First, I will briefly go through a few examples of how we draw break lines at different terrain features, with an emphasis of how we draw break lines at roadways. So first, dam embankments and spillways are very critical features to represent with break lines. In order to accurately represent dams with break lines, the break line is drawn along the crest of the dam. The ends are tied into the high ground saddle ridge that I mentioned earlier, and we pay special attention to making sure that the break lines are drawn through the dam spillway and that we capture both the highest elevation at the spillway crest and the accurate width of the spillway at the dam. Second are narrow embankments. So for narrow embankments, if any computational cells span the length of a narrow embankment, there can be inaccurate conveyance. So break lines drawn, like the one you see in the photo, along the crest of this feature prevent the water from skipping the channel. Last, one of the most common terrain features that require break lines to restrict conveyance are roadway embankments. In the example you see here, a break line has been added to the roadway crest. The LiDAR-generated terrain here has been processed to remove the bridge decking where the water flows underneath. In this case, the decking was removed from the post-process LiDAR, and we call this process hydro-enforced. So in this case, the LiDAR, we call it's hydro-enforced LiDAR. In this case, a brake line can be drawn directly over the roadway center line, and this process can often be automated. In New England, however, LiDAR post-processing often doesn't capture or remove the decking in the vast number of roadway river crossings, usually in locations where culverts, or where it didn't see the culverts or didn't remove that bridge decking. In these situations, a brake line drawn along the roadway center line creates an inaccurately high obstacle to flow. So in these cases, when a roadway crossing hasn't been hydro-enforced in a specific terrain dataset, as is usually the case in New England, a brake line drawn across that roadway center line effectively acts as a dam, constraining flow from one side of the roadway to the other, when in actuality, something like a culvert or a bridge opening would allow water to flow below the bridge. A brake line that's drawn in this way is going to, 1, overestimate the upstream flooding, and 2, underestimate the peak discharges downstream resulting from the increased attenuation from the storage in the reservoir. So to approximate the conveyance that's likely at this location, either from a culvert or a bridge opening, our team adds what we call a V-cut to the brake line. This V-cut is drawn at the intersection of the stream center line with the tip of the V at the upstream side of the embankment, as you can see in the photo. This adjustment in the brake line allows a small V-shaped opening in the roadway crest that's intended to approximate the conveyance through a culvert or bridge opening. And while we do understand that the V-cut is only an approximation of actual conveyance under an embankment, guidance from FEMA does state that the detailed representation of structures isn't required for base level engineering. Instead, representation of hydraulics in BLE has to be scalable in that if we were to attain more detailed survey data, for instance, in the future, we could add that in and update the model. So adding the V-cut allows for some of the best practices in our team, and it's an opportunity to provide the best approximate hydraulic representation of these structures with budgeted time, while still allowing for a future addition of detailed representation in the future. So to summarize some of the main approaches to handling brake lines at roadway crossings, I'm going to outline 3 different approaches and why we believe that V-cuts to our non-hydro-enforced crossings are the preferred method. So in method 1, the first method is to not draw brake lines at all. The second method which has become common practice in some regions, is to take advantage of the roadway coverage to enforce brake lines. And third, which is the method that we have found to be the most accurate and efficient, is to use a manual process which relies on engineers to draw brake lines one by one with V-cuts. So in the first approach, no brake lines are drawn, and in this case, the default orthogonal grid is used. In this case, there's no restriction to flow across or through an embankment. This underestimates upstream flood elevations upstream of a constraint and overestimates downstream peak discharges. This method is inaccurate, but it's preferred over using a centerline brake line on a roadway with the culverts in non-hydro-enforced data sets, which I will describe next. So in the second approach, a brake line is added across a road centerline without a V-cut opening. This process can easily be automated and added to a GIS roads coverage layer. However, when the terrain isn't hydro-enforced, the embankment acts like a weir without any culverted conveyance. This overestimates the upstream flooding elevations and upstream storage, which impacts the downstream peak discharges. This method is the least preferred method due to these inaccuracies. In the third approach, the brake line added at the structure is modified with a V-cut to the roadway centerline at the flow line roadway intersection. This process also does have the ability to be automated. For example, the V-cut could be automatically generated along the roadway centerline at the flow line roadway intersections. This can work in some areas of the country with, for example, a more flat and open landscape where there's a more predictable example of how roadways act as obstructions. However, in New England, where we do a lot of our work, this isn't possible because the roadways and hilly terrain quite often present complicated crossings that would require much, if not even more, manual labor to correct the attempt to automate the addition of V-cuts. So in our team, we do believe that this is the most accurate and efficient method of adding brake lines. An additional benefit to manually adding brake lines is, instead of fully automating the process, is that it allows us to easily notice some situations like the example you see here, where we have a very wide roadway embankment with lengths that span greater than the length of one 2D cell, where a V-cut in a brake line won't suffice. Here, in these circumstances, it might be necessary or easier to use a storage area 2D area connection with an approximated culvert opening. Detailed representation of culverts and bridges are out of scope for 2D BLE, so the geometry and loss parameters in these SA2D area connections are estimated, and the culverts are also only approximated and mainly used to convey runoff water downstream, just as is in the case of V-cuts. In the example shown in the figure below, the roadway embankments are too wide and tall for the effective use of brake lines, as I mentioned earlier. If V-cuts are used, they create conveyance inverts about 10 feet higher than where they should be. So in cases like this, again, it's simplest to just make, in this case, 2 SA2D area connections with approximated culverts, but more accurate inverts. In our workflow, it usually takes us around 60 seconds to create one of these approximated SA2D area connections. So in large watersheds of several hundred square miles, how do we actually go about implementing these brake lines when the number of brake lines at dams, narrow embankments, and roadway crossings often reaches into the hundreds or even into the thousands? There is no completely automated process for generating brake lines for a terrain, as I've mentioned. In New England, starting with that preliminary set of brake lines automatically generated from the road line center layer has been studied, but again, it requires much, if not more, work to add in the V-cuts and correct other errors, since most of the LiDAR hasn't been hydro-enforced. So the preferred method is to make use of our modeler's time to make accurate brake lines at prioritized locations and leaving the rest to the default grid. So while we understand that not every roadway embankment will be addressed by this approach, since there's only limited time to add and edit brake lines, it's still preferable to have the default 200 by 200 foot orthogonal mesh than to have a brake line without the representation of conveyance in the lower priority locations. So before I go on to speak about how our modelers prioritize brake line locations, I'll briefly touch on some of the visual aids that we use from outside sources in order to identify locations that need brake lines. These visual aids are all GIS features that are exported as shapefiles and then just projected to the appropriate model projection. So first, our registered dams. Each state maintains a spatial coverage of registered dams, which commonly and usually require brake lines. This layer is very important to make sure that water is contained behind the dams instead of slipping through dam embankments. Second are NHD flow lines. So while the flow lines layer isn't perfect, they do, one, orient the modeler as they navigate the terrain during the manual additions of brake lines, and they provide some guidance as to where the flow might be conveyed through the terrain. Second, they also can be used to determine where bridges and culverts might occur, and I'll discuss this a bit later. Third are roadways. So the roadway layer is exported for each state in which the model is contained. The feature classes of the roadway layers sometimes vary from state to state. They often contain characteristics like the number of lanes, the names of the roads, and the type of roads, which are all important, and I'll touch on this a bit later. Fourth is a fill depth raster. So we create what we call the fill depth raster in order to identify locations where there might be significant and sometimes inaccurate depression storage behind a terrain feature with the culvert or opening that isn't shown in the terrain. To do this, we generate this raster, and that's the difference between the regular terrain and a fill raster, which is generated in ArcHydro. The difference between the two rasters is called the fill depth, and that's the figure you see on the right-hand side of the screen. The red is the fill depth raster. The deeper red is a deeper depth. And so in a case like this, it would alert us that we might need a break line in this location. Last are the HEC-12 boundaries. They're sub-basin boundaries which orient the modeler as we're navigating the terrain. And in this slide on the bottom, I've just included what some of the data looks like as we pull it all together. You can see some of the layers, the blue flow lines layer, the black is the roads layer, and the yellow dots are some of the registered dams. So this leaves the question, how do we prioritize break line placement in a large model? Each modeler goes through several passes, which I'll describe, in which break lines in each HEC-12 boundary are created. In the first pass, we focus first on dams and spillways. So we move through that list of registered dams in each watershed, and we create break lines along the dam crests and over the spillways. Next, we focus on areas with significant fill depth from the fill depth raster that I mentioned earlier. And last, we'll add break lines at roadway flow line intersections, starting with the highest priority and moving through each of those intersections, adding break lines where terrain requires it. So it is important to note that in large watersheds in New England, the number of these flow line roadway intersections can reach into the thousands. In Taunton, there were nearly 4,000 roadway flow line intersections, so it would not be possible for modelers to draw break lines at each of these intersections. Because of this, we run a script which gives each roadway intersection a priority rating based on several of the characteristics. So in the script, larger roads, for example, interstates or US highways or state highways, are given a higher numerical score than local roads. How large the road is can be determined in several ways, and it's dependent on the available data. For the Taunton watershed, the size of the road was determined based on a road type feature. In other watersheds that I've worked on, this could be based on different characteristics, like the number of lanes in the road. For example, a higher number of lanes means it's more likely to be an interstate. The script also determines which streams are larger and gives them a numerical score based on this size. In the Taunton watershed, the size was based on names. Essentially, streams and rivers that were named were given a higher score than unnamed streams and brooks. So the numerical scores from the steps above were then added to create a priority rating for each intersection. Basically, the higher the score, the higher the priority. And then in each HEC-12, the top 40% of intersections were labeled with a priority tag to ensure spatial distribution and make sure we weren't only choosing intersections, for example, at urban centers. Following the first pass, modelers manually navigate the terrain for each HEC-12, checking as many of the remaining roadway flow line intersections as possible, as well as looking out for narrow embankments and dams that might have been missed during the first pass. The third pass and last pass is completed after the modeler runs an initial hot start run, in which the set amount of precipitation is added to the watershed and allowed to drain, filling up small depressions. At this point, the modeler checks locations with high depths. These locations are often where conveyance through an embankment wasn't accurately represented. For example, if there was a lot of water behind a roadway where we needed to add a break line. Additionally, reservoirs are checked in this location. So at this point, prioritized break lines are sufficiently added and checked within the model. So to illustrate what the break line process looks like, I'm going to demonstrate some of the steps we use to add break lines to the Taunton watershed I mentioned earlier. And finally, we'll present the modeled results from the 100-year storm compared with the results from gauge analysis, regression equations, and effective FIS reports. As described in the beginning of the presentation, this watershed has a surface area of 700 square miles, and it's located in southern Massachusetts and Rhode Island, east of Providence. Several hundred break lines were added to the watershed using our break line guidance, and in the figure, the purple outline is the model boundary. So to very briefly go through some of the data collected in the watershed, in the Taunton watershed, I will just go through some of this data, and this was all what we used to create the break lines. So first was the HEC-12 layer, that was the black outline. Second is the dams layer. This was the combined dams database from Massachusetts and Rhode Island, shown in yellow. In blue, you see the NHD flow line layer added from each state, again clipped to the watershed boundary. And last, in red, is the GIS roads layer from each state, and that's added and clipped. As you can see, the roads layer can get very extensive, especially in some of the urban areas, and this is why we did have to prioritize the roadway flow line intersections in this watershed. So as part of this first pass in drawing break lines, the roadway flow line intersections were found by taking that intersection of the NHD flow line layer and the roadway layers in ArcGIS. The prioritized locations were found using the script I described earlier, and the resulting prioritized locations are shown in the figure in pink, with all of the locations shown in blue. As you can see, there were quite a few total intersections, actually around 4,000, before the prioritization script was run. After prioritization, there were less than 1,000 remaining. Still a large number, but much more manageable. So with all of the collected data available for modelers' use, we drew the break lines in the Taunton watershed in the 3 passes I described earlier. In the figure below, I've included all the break lines in the model. You can see they were spatially distributed across the watershed, which is the result of spending an equal amount of time in each HEC-12. Last, the results of the Taunton 100-year storm are compared with the results of gauge analysis, regression equations, and effective FIS reports in the watershed. Here, I'm comparing the peak flow results at specific locations around the watershed with simulated results on the x-axis plotted against expected results on, or simulated results on the y-axis, sorry, against expected results on the x-axis. In this graph, the closer the comparison points are to the 45-degree line, the more closely the results match. This figure shows that the modeled results in this watershed match the expected results closely. So to summarize, break lines are used in our 2-dimensional base level engineering models in order to accurately model the conveyance of water through natural and man-made embankments. We have found that in New England, the manual break line addition is the most efficient and accurate method of break line application through the help of additional methods to prioritize break line placement locations throughout the entirety of each model. The Taunton watershed is a good example of a 2D BLE model in which break line prioritization was necessary due to the large number of urban areas. Through this use of prioritization, a large number of break lines were able to be drawn in the watershed efficiently, with the final 100-year storm peak flow results closely matching those from gauge analysis, stream stats, and effective FIS. So thank you for your time today, and at this point, I'm happy to answer any questions. Thank you.
I'd like to thank Kimberly for this great presentation, and we do have time for a couple questions, and I'm going to dive right into it, considering how that we're a little bit behind. The first one is from Nick. Have you considered altering the terrain as an alternative to the V-cut technology?
Hi, Nick. Thank you for the question. So altering the terrain is certainly something that we could look into. I do want to point out that in the Northeast, we have found in our models that given the scope of the project, that we can, drawing break lines has been very fast. I think it takes us something like 10 seconds to draw a break line. We have found that this is a very efficient and accurate method to alter the break lines instead of the terrain, but it is certainly something that could be done, especially in an area where you have a more uniform terrain and more text-like kind of road line, flow line intersections, as I had mentioned in the presentation. In New England, the terrain is often more complex, so it might take more of a kind of a checking and back and forth to make sure that that has been done properly. But yes, that's certainly something that could be considered as well.
Okay, and the other question we're going to be able to take is from Rick. How long did it take you to build this model, and what watershed size would you recommend limiting studies to before it becomes too complex to model?
Right. This is a very good question, and this is something that we do deal with these large 2D BLE models. And I did see a few other questions on the size of the watershed and the run times, so I think I'll just answer them all in one go. The watershed that I showed in the presentation, the Taunton watershed, was 700 square miles, and that had about 500,000 2D cells, which is quite large. I think we try to limit the models on the upper end of up to 1 million 2D cells to maintain accuracy, but it is something that we could potentially split up the watershed into 2 separate watersheds that are connected, and that's something that we consider, especially if we're seeing a lot of variability in the rainfall and the calculated curve numbers on the watershed. That's something that we can break up. In terms of the time it takes to build the watersheds, again, this does vary due to the complexity of the watershed and the size itself. I think usually to go through the whole process of building the watershed, drawing the break lines, running and calibrating, and then looking at the model results, I think it takes usually about 100 hours. But this does vary based on the complexity of the watershed. To touch on the model run times, these again vary, but they can go between, I think, between something like less than a day up to 2 or 3 days to run the model. Again, based on the complexity and the computer power that you are working with.
Okay, Kimberly, thanks again for being a speaker for us. I'd also like to thank all of you for joining us, and our speakers. All of our sessions certainly provided a lot of great information. And I'd like to remind you that all the conference sessions will be available in about a week or 2. Final thank you to our sponsor, HDR, and I hope you all enjoy the rest of the conference.